Waves 6. Sort of. I'm going to have to stop doing that. Refraction. Not to be confused with reflection or something we haven't done yet, diffraction. This is refraction. What is refraction? Well, it describes what happens when waves pass from one medium to another. Now we've done that in springs and strings, but now we're going to do it in other mediums as well. Now what happens is that because you go from one medium to another medium, the properties of the wave may change, and the most important property might be the velocity at which that wave travels through that medium. So what are some examples of when that can happen? Happens all the time. Sound going through air to glass and through to air again, light going from air to glass or air to water, all those sorts of different situations are all applicable and cases of refraction. So since V may change and we have the universal wave equation, V equals frequency times wavelength, if V changes, the wavelength must change because the frequency of the wave doesn't change, it remains the same. And so here's a scenario based on a ripple tank basically, where you have a depth of water and you have deep water, and if you insert a glass slide in here, the water here is shallow. Now we would view the wave, or the water wave would view the shallow water as a different medium from the deep water, because that's how it works. And so here you can see that you've got a certain wavelength. Here you've got a different wavelength because it's a different medium. This is an interface between one medium and another medium. The glass doesn't play any factor other than shortening or shallowing the water. So what does that look like? If we're looking down on it, here's our deep region, here's our shallow region, here's our wave fronts moving in the direction of the arrow, and there's our wavelength for deep water. And when it goes into shallow water, because the velocity of the shallow water is less than the velocity in the deep water, it condenses and makes the wavelength shorter, and so that's what it's saying here, and the frequency is the same. Now this is a classic example of why tsunamis can travel the oceans and have very long wavelengths, kilometers long, but once they start rising up onto the continental shelf and into shallower water, the wavelength changes, but it's still got a massive amount of energy, and therefore that's why tsunamis can be quite devastating, because the wavelength shortens. The velocity may actually slow down in terms of their velocity, but there's still a massive amount of energy that has to be put in that, and that's why they become quite destructive. Now let's have a quick look at an animation that shows this. Let's see if I can get this to work. I'm down here. Here we go. Let's reload this page. Okay, so here's our wave fronts coming in at V. This is half V, and so they're traveling at half the velocity, and then they come out again, and they're all parallel. So if we froze that, we can see that we're going from one medium here to another medium here, and then another medium here. And this medium just happens to be the same as this medium, but it doesn't have to be. So we can see that the waves are still being transmitted, the same amount of energy is being transmitted, but because this is a different medium, it has a different wavelength. Same frequency though. If we were to count the waves here, 1, 2, 3, we get 1, 2, 3, same frequency happening. Okay, so let's go back to where are we? Let's go back to this. So not all interfaces are at nice 90 degrees to the wavefronts. If the interface is an angle, the waves will also change direction, and this throws students sometimes. They don't quite follow how this can happen, that waves can actually bend at an interface, but they do. This is a diagram. We'll show you an animation that makes it a lot more clearer, but this is what we're trying to show in the animation. Here's our wavefronts. there's our interface, and we're going from, in this case, deep water with fast velocity to shallow water with low velocity. And so what happens is this part of the wavefront hits the interface and slows down, so the frequency stays the same but the wavelength shortens, and whereas the rest of the wave keeps proceeding until it hits the interface and then it slows down. And so the net result is that you can see here the angle of incidence, and the angle in this case, let's just write this angle here is the angle of refraction, not the angle of reflection, and this still is the angle of incidence. Nearly forgot how to spell incidence. And it's always measured to the normal, and the normal is at 90 degrees to the boundary. Forget about this line, that's unimportant. Forget about this line, it's unimportant. Hope we get that? So it doesn't obey the law of reflection, where the angle of incidence is equal to the angle of reflection. In this case we have an angle of refraction. Right, let's get rid of all that. And so here's another example. Again, this is the interface we're worried about. Here's our waves going in this direction from left to right. They've got a short wavelength and they get bent quite dramatically into this direction here, and this will be our angle of refraction relative to the normal. Okay, and so here we're going from fast to slow, and so you can see here that the angle direction of propagation is bent towards the normal. Here we're going from slow to fast, and the angle of propagation is bent away from the normal. Good thing to remember. Let's have a look at this animation. I'll swap over to my mouse and I'll push this, and we'll do this one here. Here we go. Let's reload this one. So here we have one velocity. Here's our wavefronts. This is 2/3 the velocity, and notice the bending, and we can pause it at any time. So this is still the same wavefront, but because this is traveling slower, it has this kink in it, and then it becomes a straight wavefront, and then it will kink again. And of course these two interfaces, this one and this one, are parallel. The incident waves and the refracted waves go off in the same direction. They've just been stepped across a little bit. Okay, but if these weren't parallel, these waves, the refracted waves, would not go off in the same direction. And when we pull out the light boxes, we'll see that in class. Alright, so let's go back to PowerPoint. Hopefully that made that all clear. And here's a photograph from a ripple tank, and if we drew on it, there's our interface just there. There's an incident wave, and there's a refracted wave, and there's a refracted wave. There's an incident wave. Something weird's happening over here, but we don't get confused by all the extra noise. Alright, that's what we're trying to show. So you should now be able to do question 9 in your workbook, and in the next video we'll learn about diffraction. See ya.